I promised an applications video, and here is an applications video. Let's do some applicating. Okay, I love this joke. I'm not sorry. Applications of eigenvalue problems. There are so many. They're all over the place. This is one of the most ubiquitous applications of linear algebra just in everything, in science and engineering, in math, like you name it. To list a few, when we are solving for energy levels in quantum systems, so think like band structure in semiconductors, think about active layers in solar cells when we are talking about spin states in magnets and like alignment, anti alignment of domains. All of those can be represented by matrix problems. And there's a particular matrix, it's called the Hamiltonian. It's named for Hamilton, but not the musical, like the mathematician, and the eigenvalues of that energy operator, that energy transformation matrix, those eigenvalues are the energy levels of your system. So this is how we find the energy levels of quantum systems, is by solving eigenvalue problems. Now, another quantum application, and one that will actually work out in some detail today, is looking at electron spins. Electron spins are so important. You know this even from chemistry, right? That the pairing of electrons in orbitals gives you all sorts of effects like splitting of energy states and formation of molecular bonding orbitals and determining the filling order of orbitals, which leads to available bonds and is one of the reasons why transition metals are so weird in so many ways. There's lots more actually that you maybe have not learned about before, like interactions between the electron spin and the nucleus of the atom that it's orbiting. Those spin-spin interactions, because the nucleus has spin also, those drive some of the finer structure of energy levels in atoms, which also affects bonding and therefore chemistry and materials and blah, 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 blah. It's electrons, man. So we'll look at spin states of electrons in detail today. The other example that we'll work out in detail today is looking at rotational inertia in solids. So this is something you see a little bit in Physics 140 and maybe in ME 211. I want to give you a better toolkit for understanding rotation in terms of eigenvectors and eigenvalues. Some examples that we'll look at later this semester as the time goes on, we'll look at three-dimensional stress and strain. So not just like engineering stress force over area, but actual stress fields in solids, and looking at how we can understand these things in terms of eigenvectors and eigenvalues. This will be really big helpful. Really big helpful? What? Okay, this will be helpful bigly for MSE 420 in particular. We'll also look at vibrational states later this semester. This is really important for certainly how sound propagates through solids. And so this leads to acoustic properties of materials. It also is going to have effects on even things like vibrational frequencies of bonds. If you have not just network solids, but even smaller molecules, then the vibrations of those molecules, which anyone who is taking or has taken my lab class knows that with infrared spectroscopy, we can measure a lot of bond vibrational frequencies. Those can be expressed in terms of eigenvalues. When you look at conductivity in materials, whether electrical or thermal, but more traditionally electrical conductivity in solids, you actually don't just have a conductivity number. Once again, there's a conductivity matrix because some materials are anisotropic. They have different properties in different directions. And this anisotropy of systems is really one of the big indicators of when an eigenvalue approach to a problem is going to be useful or maybe necessary, because once different directions are behaving differently, this often is going to be related to the eigenvectors of some matrix. So if you have like a composite or even just a very directional solid like graphite, for example, conductivity between layers of graphite is very different than conductivity within layers of graphite, because, those layers are bonded between each other with van der Waals interactions, whereas you have all of these somewhat delocalized covalent bonds in the hexagonal network of the graphite sheets. And so, with all these delocalized electrons in these hexagon rings, there's a lot more opportunity for electricity to flow, which is why graphite is a good conductor. And we can express that in plane versus between plane difference in terms of eigenvectors and eigenvalues in the plane and out of the plane. Okay, but I promised two in detail today. So before I just go on forever, let's get to it. Let's look at the spin of electrons. So for those of you who have seen MSC 242, this will be hopefully review, or at least somewhat vaguely familiar. If you have not taken any like physics of materials or PChem or quantum physics or anything like that, this will be totally new. And honestly, half of it will make sense, half won't. That's okay. First time seeing this stuff is always a bit of a trip. For that matter, second and third time seeing this stuff is a trip too. So electrons have angular momentum intrinsically. Every electron in the universe just carries angular momentum by virtue of its own existence. And the magnitude of that angular momentum is h bar over 2. So that's Planck's constant over 2 pi over 2. And I already said why this is a big deal. So what I want to show you how to do with an eigenvector approach is to start to express spin states of electrons, not just in terms of up and down, but actually in 3 dimensions. Because, atoms are 3-dimensional. When we're doing chemistry and we're doing orbital filling, it's like, it's spin up or it's spin down. Well, I mean, yeah, kind of, but again, the universe is complicated. So we need more sophisticated tools to really gain a full understanding of what's going on. And in order to do this, we write spin matrices. These are called the Pauli spin matrices. These were actually invented by a white European, like really. So I didn't think to put a picture of him on a slide. Pauli was a very interesting character, Wolfgang Pauli, but that's a story for another time. Invented the nuclear reactor also with a large team of people, not just by himself. Okay, so Pauli spin matrices. There are 3 of them. And these are matrices that are going to be used to understand spin in the x and y and z directions. And if you look at them, they have some similarities amongst each other, but they're all distinctly different as well. The z looks almost like the identity matrix, but not quite, because instead of 1, 0, 0, 1, it's 1, 0, 0, negative 1. So that is going to come back very soon. And for the x and y, well, the x is, yeah, like it almost looks perpendicular to z. That's just an analogy, don't overthink it, but you can see that like z and x are not overlapping with each other. But then y, what is going on here? Why is the imaginary unit in a spin matrix for a real electron that's in the universe spinning? And the answer is because imaginary numbers are not imaginary. They exist in the physical world. The wave functions of everything that exists are complex valued. It's so unfortunate they got the name imaginary because they're anything but. They're some of the most real stuff that there is. So this is why I know I'm a little bit weird like this, but I really harp on using the terminology complex number instead of imaginary number because they are complex, but they're definitely not fake. Okay, rant over. It's going to be one of those days, guys. Just buckle in, grab a tea, whatever. Okay, so these matrices will tell us things about directionality of spin and systems. Let's do some math. Well, we'll solve for the eigenvalues of spin x. And so we write our characteristic equation, determinant of matrix minus psi lambda equals 0. Hopefully you remember that from the last video. And because we have zeros on the diagonal, 0 minus lambda is real easy. And that means that this polynomial is very easy to write as well because the forward diagonal is just lambda squared, backward diagonal is just 1, forward minus backward, lambda squared minus 1 equals 0. And this is a super easy polynomial to solve. You can probably do this in your head if you stare at it for a second. You're like, oh, lambda has to be either positive or negative 1. Now, it can be positive or negative 1. That's true. That's very important because electrons can spin up or down, or in this case, they can spin left or right. And that positive or negative one is the direction of the spin. The one is the magnitude. Actually, it's in terms of h bar. So h bar over 2. But yeah, these are the roots of this polynomial. And there you go. So this result tells us, again, that spin is quantized, that it has one of two values, this way or that way, nothing in between. And let's find the eigenvectors that correspond with these eigenvalues. Okay, the eigenvectors of the X spin matrix. Well, we write our eigenvector equation. Matrix times eigenvector equals, and then implicitly in here is the eigenvalue. It's just the eigenvalue is 1, so I didn't write 1 times. And this gives a very simple equation. That equation is y equals x, so our vector is 1, 1. And just like last time, there's actually infinitely many answers, but usually we just pick a value that's simple and roll with it. And then the eigenvector for the other eigenvalue, the negative one, is, well, 1 minus 1. So you're like, well, what do these vectors tell me? These vectors tell you the direction in which the angular momentum of these x spinning electrons is pointed. And it's not along the x-axis. That's weird. It's a mixture of x and y. So again, for those who have taken 242, this idea of superposition states, this is where it really starts to manifest in a very clear way in linear algebra terms. A superposition state is a state where the state vector of the system just has multiple non-zero components. It has some amount of each of those things all at the same time. And if you've never taken quantum and you're like, what is happening here? It'll be okay. We'll get through it together. Let's look at the Y matrix. This is now just for practice, just for, showing more examples of working through the calculations. So you write your characteristic equation, you put in your terms in the matrix, you take the determinant. The determinant is still lambda squared minus 1. Now, careful with this. The minus I times I here gives us negative I squared. Negative I squared is positive 1, but we're subtracting that from, so it's like minus, 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 right? We're subtracting that from the forward diagonal. So it is still lambda squared minus 1 for the polynomial. And that means that lambda is still plus or minus 1. Our eigenvectors, well, we'll see about that in a second. But what's interesting here is even though the matrix was complex valued, the eigenvalues of that matrix were purely real valued. Now, it is possible for a real matrix to have complex eigenvalues. It is possible for a complex matrix to have real eigenvalues. It is possible for a complex matrix to have complex eigenvalues, blah, 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 blah. All of these combinations are possible. But what's really interesting is this. This is like a big, head explode moment. I should put head exploding guy GIF in the slide. What am I doing? Okay, imagine you're seeing head exploding guy GIF. When you have these matrices, like these spin matrices that correspond to physically observable quantities, like quantities in the universe that you can poke with a stick and say, hey, what's the value of it? The eigenvalues are always real, because even though wave functions in the universe are complex valued, every time you measure any measurable property of a physical object, you always get a purely real answer. This just seems to be baked into the structure of the math of the universe at a very fundamental level. So what we'll find is that our eigenvalues are always real, and this indicates that the spin of an electron is always a real number. When you solve for the eigenvectors, this is where it gets funky, because we have an eigenvalue of plus 1, again, implicitly written in here. And so then that means y equals ix, which means that the eigenvector of this thing is 1I. Now, that's not just like a direction in three-dimensional space. What does that mean? It has a meaning, but we have to get into like a much higher level quantum mechanics course to unpack it. So for now, just see this as an example of a calculation. I've taken this about as far as I can in explaining without doing a whole quantum class first. But if you have a little familiarity with this and you're curious to know more, Tell me you're curious to know more. I love this stuff. We can talk about it all day. It's great. Okay. I didn't write out the solving of the z ones because that's very easy. It's just 0 and -1. Or sorry, it's, oh my God. It's so easy I can't say it right. The eigenvalues of the Z matrix are just 1 and -1. Again, spin up or spin down. And then this is where I'll try to say one more thing a little coherently, which is that if you look at the eigenvectors of the Z spin matrix, so this one and this one, those eigenvectors only have one single non-zero component. That means that when the electron has spin up in the z direction, that it is not in a superposition state. It only has one single spin value, and that spin is exact and it's uniquely resolved. And that is different from these x and y things, which are superposition states. Okay. What does this all mean? I am trying so hard. Sometimes the physics brain just gets going and I can't reel it in. So in writing, here is some of the stuff that I've been saying in words. So I'm actually just going to be silent for like a few seconds and let you read. Of course, you can pause it as well. Okay. So quantum mechanics is great, and the language of quantum mechanics is linear algebra. Oh, all right. Time to move on to my like least favorite subject ever. I do not like this stuff. I admit it's very useful, and I'm glad other people like it because someone has to do this. I just really don't want to myself. And you know what? I feel like we should be able to talk about these things, right? To say, hey, I'm actually not interested in that. But also, even though I'm not interested in it, I'm still going to go ahead and learn about it because I acknowledge that it is an important thing. So, this is my take on rotation, basically. And this definitely is not like me still having lingering salt from the fact that I got a 28 on my first exam in grad school in mechanics. And yes, that is a 28%. And look at me, I graduated just fine. So quit freaking out about exams there. What was I supposed to be talking about? Rotation matrices. Rotational inertia. Okay, there it is. Also, let's shift gears. That's funny, right? Because gears rotate and we're talking about rotation. I'm sure you're laughing at the joke. I can't hear it, but I believe it in my heart. Oh, man. So physics, torque, I omega. And you're like, wow, this is literally Newton's second law, right? F equals ma, torque equals I omega. It's just one of them is linear and one of them is rotation. I'm super over it. Well, let's give this a second chance because this torque and rotation equation, oh man, there's a typo here. What have I done? Torque equals I alpha. Sorry about that. That one slipped through my proofreader, who is me. Okay, so torque leads to angular acceleration, just like force leads to linear acceleration. So what's the big deal here? The big deal is that this is actually not just a scalar equation because torques exist around some axis of rotation. The direction of the torque is a vector. Well, the torque is a vector and it has a direction. And there it is again. Ta-da. And the angular acceleration also has a direction. Angular acceleration is a vector quantity. The direction is the axis that the rotation is accelerating around. And you're like, okay, so vector, number, vector. No. I is, I am, I is, it always feels wrong to say that. I is the rotational inertia matrix of the system. This is not just a vector equation. This is actually a matrix equation. And the rotational inertia of a system has 9 different components. There's the component of its x inertia when rotated around the x axis. It's the x inertia rotated around the y-axis, the x inertia rotated around z-axis, the y inertia rotated around the x-axis. I'm going to stop there. So we need 9 different numbers to actually describe the full three-dimensional rotational mechanics of systems. And rotation's a big deal. Like, if you have taken ME211, you know this is really important. If you have not taken ME211, well, you're gonna have to swallow that pill at some point. So what am I trying to get at here? How does this relate to eigenvalues and eigenvectors? Well, here it is. The eigenvectors of this rotational inertia matrix, those are called principal axes. Those are special directions in the rotational motion of the system. Usually it's either a symmetry axis or it is an axis that the rotation is stable around. So it's indicating that if you spin your system around this particular axis, then what will happen is that rotational motion will be stable and won't, well, become unstable. So then the eigenvalues are the rotational inertia or the moments of inertia around those principal axes. There's one more thing I want to point out here, and then I actually have an example that I hope will help people. So there's this thing called the figure axis. The figure axis is the principal axis, the eigenvector, that has the highest inertia value. So the eigenvalue associated with that eigenvector is the biggest eigenvalue out of the set of eigenvalues that this matrix has. And so the thing that's special about that direction is because the inertia is very high around that rotational axis, rotations on that axis tend to be very stable. So the example here is, imagine a tennis racket or a racquetball racket or a badminton racket, whatever. Like, I mean, it's even true for a lacrosse stick, but less true for a lacrosse stick. But imagine a tennis racket. There are 3 different ways that you can spin a tennis racket. You can spin it around the handle. You can lay it down on a table flat and spin it around flat in that plane. You can tumble it end over end, where the handle and the head of the racket are rotate, or really like orbiting around each other. So we have these 3 different rotations, but think about it like physically, just from your own experience, which of these is the most stable? Which of them doesn't go flying off and become chaotic? It's the rotation on the symmetry axis of the racket. And this would actually come out of the eigenvalue analysis. Now, we're not going to do a tennis racket example because calculating the rotational inertia of a tennis racket is going to involve some nasty integrals that I do not want to do. And I don't want to make you do it either. So we're going to look at a cube. Cubes are less exciting, but also much more tractable. So this is a result you can actually just look up on the internet. It's possible to calculate this yourself. Maybe you'll learn how someday. I'm not that fussed about it, to be honest, because I want to get to the point of the example and the physical understanding that comes from solving this kind of eigenvalue problem. So here's the rotational inertia matrix of a cube rotating around its corner. The side length is b, the mass is m. And I've just factored out this mb squared over 12 term because that makes the matrix look really nice. I'll have to remember to keep that factored coefficient in my calculations, but doing this kind of initial factoring can make the math much easier to do. So I recommend it as a strategy when you can. And if you look at this matrix, the matrix itself is symmetric. We have these 3 diagonal components that happen to be all the same as each other. And then when you look across the diagonal, the elements in corresponding positions across the diagonal are the same as each other. So matrices that have these symmetries are much faster to do calculations with. So the question that came up a few days ago, people asking like, when is it a good idea to invert matrices? Well, if it's highly symmetric, there are tricks you can do to invert it much faster. We're not doing a matrix inverse, that just came to my mind. So what are the principal axes of a cube rotating around its corner? Well, here's the math. So this is our matrix minus I lambda, write the characteristic equation, take the determinant. This is going to be a cubic equation. And now we get an example of degenerate eigenvalues. So this is this thing that I mentioned last time, that when you have third order, fourth, higher order polynomials, you can get repeated roots. And in this case, we get the lambda equals 11 value twice. Then we also get the lambda equals 2 value once. So lambda equals 11, that is a twofold degenerate eigenvalue. Fancy vocabulary, but it means that eigenvalue occurs twice. There are two different directions that both have that particular moment of inertia around that axis of rotation. Okay, and then going from there, we have to remember the mb squared over 12 coefficient that I factored out, and now we've got the three moments of inertia around the three principal axes of the system. But what are those principal axes? Well, you find them by solving this series of equations. We have our initial matrix. I'm looking at the lambda equals 2 eigenvalue here. And so matrix times vector equals eigenvalue times vector. You write your equations. There's three of them. You're going to solve them. You're going to have to choose one value because there's infinitely many solutions. And so you choose like x equals 1, for example, and then go from there. I'm glazing over this because I've been talking for actually quite a long time. I feel a little bad about that. I just get excited about this stuff. Okay, so let's wrap it up. When you finish solving those sets of equations for your different values, what you find is for the unique eigenvalue for this one, we get the eigenvector 1, 1, 1. So that is this. Forgive my vector being drunk. It's trying its hardest. So that's the 1, 1, 1 direction, and that is from one corner of the cube to the other. And it makes sense just physically that that should be a special direction for rotation in the cube. That's kind of like the center line of the cube. And so if you spin it around that axis, that should be a motion that is more stable than just spinning it around any arbitrary point somewhere in the middle of the cube. And then for the degenerate eigenvalues for this repeated 11, we find different sets of solutions, linearly independent eigenvectors. This is the other thing that I mentioned last time. When you have a repeated eigenvalue, you can find multiple eigenvectors associated with that eigenvalue that are linearly independent of each other. And in this case, again, there is a real physical meaning attached to this. So here's our 1, 1, 0 direction. Here's our 1, 0, 1 direction. And sorry, I definitely just drew that wrong. I have been talking for too long. Okay, let's try this again. What am I doing? Oh, I drew both of them wrong. That's the problem. Sorry about that. Let's try this again. I don't edit out my mistakes. It's important to show that people make mistakes, right? This is part of the process of learning, is doing it wrong, realizing you did it wrong, and then doing it right, or at least doing it better. Okay, so -1, 0, 1. So that is, there we go. That's this direction. And then -1, 1, 0. That is the corner to corner along the bottom face of the cube direction. So these are the three special axes. And so one of them is the diagonal from corner to corner. And then the other two are the face diagonals, the diagonals from corner to corner along one face of the cube. And again, it kind of seems reasonable. If you take a cube and spin it around one of these directions, that's a more symmetric action than just grabbing any random vector somewhere through the cube. So in this case, that's what you get out of that. All right. I did not mean for this one to go on this long. Thank you for your patience and endurance. I will do my best to contain myself a little bit better next time. I'll see you in class.